Ever wonder how AI models really learn? Like, how do they figure out patterns so well that they can handle tasks they've never seen before? Today, we're diving into a groundbreaking study that's cracking the code on how some AI models generalize. That is, apply what they've learned to brand new situations. Let's start with a simple idea. Imagine a team of specialists. Each expert in the team is great at one specific task. Maybe one handles math, another deciphers language, and a third recognizes images. Now picture a router that decides which expert to call on for each problem. That's the core of a mixture of experts, MOE model. It's like a smart team, where the right specialist jumps in at the right time. But here's the twist. This research isn't just about how experts work individually. It's about how the router, the system that assigns tasks to experts, shapes the whole model's ability to generalize. Think of it like a conductor guiding an orchestra. Even if each musician is talented, the overall performance depends on how well they're coordinated. The study introduces something called a routing kernel, which mathematically measures how similar two inputs are based on which experts they trigger. If two questions end up routed to the same set of experts, the model sees them as similar. But it's not just about the router's choices. It also factors in how those experts actually perform on the data. It's like saying, hey, these two problems hit the same specialists, and those specialists are really good at handling this kind of task. Now here's where the science gets really cool. The researchers proved a generalization bound, a mathematical guarantee about how well the model will perform on new data. They showed that the model's error depends on three key factors. 1. Bias, how well the model's structure aligns with the problem. 2. Variance, how sensitive the model is to random fluctuations in the data. 3. Noise, the inherent unpredictability of the real world. The magic happens in the routing kernel itself. By combining the router's decisions with the expert's capabilities, the model can adapt more effectively. It's like having a flexible team, where the router dynamically assigns tasks based on both the problem's needs and the specialist's strengths. What does this mean for AI? It suggests that the way we design these teams of experts, and how they're guided by routers, could be just as important as the experts themselves. This work isn't just theoretical. It's a step toward building AI that's not just good at memorizing data, but truly understands it. But here's the thing. Even the most elegant AI models face real-world hurdles. Think of it like this. Imagine a medical test that detects a disease with 99% precision in a lab. When deployed in a clinic, factors like patient variability, equipment calibration, or human error can throw off results. Researchers had to ask, how do you make a test reliable under all these variables? Their answer: they didn't just run more experiments, they simulated real-world chaos. Think of it like testing a parachute by dropping it from a plane, not just a lab bench. They tweaked the test's design, added safeguards, and even trained users to minimize mistakes. The result? A system that's not just theoretically sound, but practically robust. So whether we're talking about AI or medical diagnostics, the lesson is the same. Science isn't just about what we discover, it's about how we make those discoveries work for everyone. These challenges might slow things down, but they're what push us to build smarter, more resilient solutions. After all, the best ideas aren't the ones that look perfect on paper. They're the ones that hold up when the real world kicks in. Thanks for watching. If you want to dive deeper into how AI thinks, hit subscribe. Stay curious.